Paul Elliott is the head proprietor and head bottle washer of Turn Island Systems. And he has the sexy hardware, and he has the pleasure of being able to say that his stuff is deployed certainly in Antarctica, but is in ships also?
Yeah, we've got stuff little company I have called Turn Island Systems, and we make gear. This is not a Turn Island advertisement. I won't be talking much about it, but do have multi-channel low power transmitters, that are used for ionospheric research. If you're interested in that, talk to me here or later about that. There's an organization called HAMSCI, HAMSCI, that I'm particularly involved with. And again, ionospheric propagation research. I make stuff that is used for that. And a lot of other gear is used for that as well, not just things I make. But I've got a multi-channel transmitter, one's down in Antarctica, German base. One's practically at the North Pole, a Canadian, again, mostly science, research centers. Got one on the grounds of Fort Collins, Colorado, WWV, just because it's a nice place for a reference signal. And actually, lots of other places too, ham stuff. But I'm not here to talk about that. So I'm going to be talking about SDRs. Most of what we've been talking about is web physical, familiar with the 7-layer OSI stack and all that, or I had to be anyway a long time ago. And this may end up being, there we go. Okay, how about that? That looks maybe like, okay, well, I see something here. There we go. And slideshow. Okay, so, you guys have been way up at the application layers and all that up. And I tend to play down at the bottom of the stack, the layer 0 stuff. If you lift up the rock, you'll see me down there. And below, it's kind of turtles all the way down, really. But we're going to be talking about the stuff that I have learned or other people have learned and told me about how to optimize software-defined receivers in the HF band. And in particular, the receiver that we're using mostly is it's a very simple SDR, but it basically covers from 10 kilohertz up to 60 megahertz wideband, continuously, that entire spectrum. And some people are and that used, thank God for USB 3, very high speed. I'll talk about that a bit more. But things we've just been discovering or finding out. Anyway, dynamic range, noise, aliasing, that's a sampling receiver, and frequency stability, because that's critical in the ionospheric research we're doing. And let's see, can I move to the next page? So me, I'm here, I'm wearing my Turn Island Systems hat, but I also am vice president, Tapper board. I'm a retired engineer. Mostly it was telecom, fiber optic, digital, but I've also done RF work. And it's pretty amazing. The data rates we were doing and the fiber stuff was faster than the carrier frequencies I used to work with VHF FM. I've been a ham since probably, I think, 1975, a long time. I don't really use the radios. I've got them, and occasionally, once a year, I'll find the microphone and make a contact. But I've been retired for about 25 years now. Got lucky, so I was able to do that. But I'll always be an engineer, afraid to my wife's dismay. So I just do this stuff because I love doing it. SDR receivers, okay, we've already seen, previous discussion, presentation. It's kind of a game changer. It's interesting though, the full bandwidth receivers, like the ones that we're using to cover the entire HF band and 6 meters as well, if we set them up like that, they require a different type of optimization as opposed to traditional ham, channelized or single band at a time receivers or transceivers, where you can get filtering that, if you're interested in the 40-meter band, you get the 40-meter band, and then you also get some analog filters, crystal filters and whatever to get rid of the stuff you don't want to listen to. And then once you've got that, it's a much easier job to deal with dynamic range. And dynamic range is important because of amplifiers get overloaded, mixers get overloaded, the analog stuff gets overloaded, but the digital stuff also gets overloaded. Also, SDRs, you've got Nyquist, one of my heroes. But you need to understand Nyquist sampling theorem. We heard you have to sample at twice the highest frequency, signal content of your input. Actually, you can undersample if you're interested, and you can work on the folded back spectrum, the alias spectrum, and a lot of times, not what I'm talking about here, but you can do cool stuff with Nyquist if you want. And the ionospheric propagation research, we're measuring Doppler shift stuff that's going, up, refracting off the ionosphere, coming back down, sometimes multiple paths. And we can learn a lot about what the ionosphere is doing. And that's the science part. By measuring the frequency, we know the transmit frequency, and this is down to millihertz or in many cases microhertz. And if we know if the receiver is an accurate frequency measurement, we can measure the Doppler shift, and it can be many hertz of Doppler shift. And the better we can measure that, the better our data. So here we are. RX 888, if you're not familiar with it, it's actually a pretty simple SDR. It has a mixer and a VHF input, but we're not using that for the research I'm involved with. And I'll be using this as an example, but these apply to most other SDRs, at least to some extent. Inside the 888, okay, good. It's got a low pass filter. That's an anti-aliasing filter. Notice the local oscillator, 130 megahertz. That's a little bit more than twice as fast as the 60 megahertz low pass filter. It has a variable gain amplifier. It also has a attenuator, but that actually generally we shut that off because it doesn't really add anything. And it has a 16-bit analog to digital converter. Goes through USB 3 interface into a computer that's running KA9Q radio, and usually an application called Whisper Daemon. And I'll have links if you're interested at all in participating, or you just want to know more about it. Some really smart people have done a lot of work in this. In the 888, the low pass filter, well, it kind of sucks actually. It's not really good enough. So even if you're running at the full clock rate, stuff like FM broadcast bands, 88 and 108 megahertz, and I'm talking about US interference, that will still get through the filter, if the signal's strong enough. And so we have to pay attention to the front end filtering on this, just for Nyquist. That's and a little bit more than that too. Also, so the analog digital converter is 16 bits. That is a 96 dB dynamic range. In theory, in practice, it's actually a little bit better than that because of issues like undersampling. You narrow the bandwidth post-processing, and you have dithering on the input, and we've got natural dithering at the input because of background noise, because of all the other signals that are occurring. So We actually get better than 96 dB dynamic range, but that's, you know, not a whole lot better, but somewhat better. Here we got noise floor. You've probably seen this before. The takeaway here is that noise is worse at the lower frequencies. Now, you VHF and UHF nuts, you don't have to worry about that too much. Your front end noise, the semiconductor noise is probably the limiting factor there. And all this depends on your antenna too. But down at the HF region, the background noise, which is mostly, a lot of it's just global lightning strikes, but there are other, and to some extent, galactic noise, but these days, and so there are three curves here. You probably can't see the fine print, but one at the bottom with the dotted curve, that's quiet rural. And the one at the top, the solid line, that's residential. And that's because, and it's probably worse than this chart shows. Generally it is, because we all have switching power supplies, solar panels on the roof, whatever. We live in a noisy world these days, and it tends to get worse at the lower frequencies. That straight line at the bottom, that is the noise floor of a typical receiver. And whenever we talk about noise floors, you need to know what the bandwidth is that we're using. And we'll have, I won't go too deep, but anyway, this is a standard. It's been measured with careful equipment and all that. And then the 888, we can look at noise floor and we can look at signal strength. And you can see that as we increase the attenuator on the 888 input, the noise floor gets worse. Signals, we do that if the signals are strong, but we're going to reduce the gain, AGC, digital AGC, because we have a strong signal that would otherwise overload the analog to digital converter. Well, this is a wideband receiver. We might have a strong signal somewhere, but as we reduce the gain, increase the attenuation, we are killing the other weak signals that we would also want to hear, because we're trying to listen to 60 megahertz full bandwidth simultaneously. More stuff, RX 888 measurements. The takeaway here is really dynamic range. We're seeing on the far right-hand column. Oh, my mouse, is that going to work? Yeah, you can see that there. These numbers here, that's really what we want to look at. And the best we've got is 114 dB. So that is the dynamic range. Just keep that in mind. Here's some real-world signals. Again, HF. This is not a calibrated measurement antenna. This is just a off-center dipole I had outside my bedroom window. And that green hash at the bottom, that grass, that's the noise floor of my spectrum analyzer. A actual receiver would probably be 20 dB better than that. And I live in a quiet area. I live up in the San Juan Islands, 70 miles north of here or whatever it is. But even there, so you can see the tendency at the low frequencies for the noise to get worse. The two signals I have highlighted there, WWV at 10 megahertz, WWV at 10 megahertz, and an AM broadcast band station. It's a small 500 watt station, but even there, you can see, and then you look away up at the higher frequency end, and quiet signals, what your noise floor might be. And there's a pretty good dynamic range there, but in the US, actually in Europe, it's even worse. But in the US, we've got AM broadcast band. That tends to be the killer at HF. And for your typical receiver with my antenna here, if you had a strong clear channel station, 50 kilowatt, 20 miles away, the dynamic range would now be 117 dB. That's beyond the limit of the analog to digital converter at best case in the 888. And again, that is a 16-bit analog to digital converter, and size does matter here. Some of the, I think that little SDR, web SDR, that might just have an 8-bit. Maybe they bumped it up. I've got a bunch of those. And there's a number with 12-bit analog to digital converters. And they're all useful, and I've used them, and I've done cool stuff with all of them. But when you're doing full spectrum, wide dynamic range stuff, more bits matter. So what do we do about it? Input filters. And I've developed a number of input filters, turn island systems, because we needed them, and they weren't, these specific ones were not available. We needed them for the ham side groups. So there's two parts of the filter that I've been putting out. Low frequency shelf filter, which attenuates, starts at about 10 megahertz and it gets more and more attenuation down to about 20 dB below megahertz. And that's really kind of complements the atmospheric noise, the way the atmospheric noise rises. The intent is to kind of equalize signals across the entire 60 megahertz range. And it also knocks down the AM broadcast band stations pretty well. Also, I have an excellent, if I say so myself, anti-alias filter that kills the FM and television broadcast bands, or even the got a 30 megahertz that kills like police radio and stuff like that, which can really interfere. I got some with preamps. In a lot of cases, we use a preamp because the AAA and a lot of SDRs, their sensitivity maybe isn't what it could be. So a little bit of preamplification is good. Too much is definitely not good, but the proper amount of preamplification can really improve things. Yeah, there's a filter or a filter with a preamp that I do. Notice the little blue boxes. That might have been the hardest part, is getting the mechanical stuff done. This is the response to the filters. You can see, and again, Turn Island is not the only outfit that can make a filter like this. You can buy similar ones, maybe not the shell filter, but you can buy them. And there's no magic in my designs. It's all standard textbook stuff. But I've got, a low noise, high dynamic range preamp in there. I've got filter. Notice the bottom of the chart here. That is the shelf filter. It's a 2-section, and in this filter, you can bypass one of them. And you can see how the attenuation, the gain falls off, or the attenuation increases at the lower frequencies. Again, I think I'll show you. Yeah, here we go. This is taken at a different time of day. So instead of 10 megahertz WWV, I think I have 15 megahertz here. But the AM broadcast station is still there at the bottom. Up near the top, just as a reference, is 15 megahertz WWV. And you can see how the shelf filter has dropped the FM broadcast station by about 10 dB. And it's raised the 15 megahertz WWV signal by about 10 dB. So that's about a 20 dB dynamic range equalization in this case. Well, actually, it'd be in any case, really. I mean, what your receiver sees depends on what signals the world is throwing at it, but this is what's happening to the effective gain. And 20 dB is a big deal. Here's another filter, 6-meter filter preamp. This one happens to have 20 dB of gain. But you notice around the 88 to 108 megahertz. Yeah, I don't know why that's popping up. Let's see if I can avoid it. Yeah, well, okay. 88 to 108 megahertz region. I diddled with the filters to put the notches, the zeros, right, or 88 and 108 megahertz basically. So we've got better than 80 dB of FM broadcast band rejection, which in an environment where you're close to an FM transmitter or a TV transmitter, that can really make a big difference. And okay, in Europe, HFMF broadcast, really HF broadcast stations, they're pretty common in Europe, not so much in the US. But I'm sorry about this pop-up here. It's a real problem. I don't have a good solution for it. People will use notch filters specifically tuned to, one or two stations that are giving them particular grief, but it's a hard problem. More dynamic range on the analog to digital would help. But again, for this wideband stuff, we don't want to do general purpose, we don't want to do narrow filtering because we're receiving everything simultaneously. Now I'm going to get a little bit geekier here. Frequency accuracy, we need, again, for the science and also for some of the other modes, moon bounce, I assume, but these narrow bandwidth modes do require high stability on the transmit and receive signals, and a lot of with a transceiver, that's a particularly hard problem because you've got a power amplifier that's heating up inside the same box as your, ovenized crystal reference if you're lucky. But as the thing get hot, heat up and cool down, the frequency will be drifting. And some of the modes, small fractions of a hertz make a big difference. So we need to improve or have adequate accuracy for the task at hand. For a lot of purposes, what's off the shelf works, perfectly well. But in other cases, we need tighter frequency control. So there's drift and wander, which is, and phase noise. These are all frequency or phase variations. The accuracy is more if I set it to 10 megahertz, is it actually 10 megahertz or is it, 10.007 or something? And then the drift and phase noise is how much does it vary from whatever frequency it nominally is. And then there's spurious, and a lot of what we're doing uses clock. I'm sorry, I keep looking at this stupid thing. Use clock generator chips, I heard DDS mentioned, which is direct digital synthesis. And again, that's very commonly used type of clock generator, frequency generator. And these are all factors. And this is more, if you're designing this stuff or if you just want to understand why things are done the way they are, these are the kind of things you're going to look at. Here is, did some work with the QRP Labs QDX, little tiny transceiver black box thing. Again, HF, it's a brilliant little design, but it has a nice TCXO, temperature compensated crystal oscillator, inside the box. In most cases, that stability is just fine. But some of these digital modes, and here you're seeing, it's one of the FST4W modes. I think it's -1800 or something, but it takes about 30 minutes to transmit its sequence of, its data. Every frame, again, takes 30 minutes, and the frequency shift, that's a small fraction of a hertz. And here we're seeing it's 4-level FSK. And that's a measurement I made on equipment that I designed. And here you can see as you start transmission, the frequency goes up for a little bit and then it starts dropping. And then finally stabilizes more or less out, after half an hour, whatever it is. And in this mode, that is a completely undecodable signal. That mode does not do frequency tracking. Whisper does. Whisper will try to follow the drift in your signal. This mode will not. And so you can't get there from here with this. Did I say anything else about that? Well, ended up back up again, maybe. Yeah. Um, I worked with Hans and some other people. Hans, the guy that runs QRP Labs, really nice guy. And we tried a couple things. There were some other issues with it, and he was able to do a spectacular job of fixing those. But the frequency drift was just could not be managed. I tried various, heat sinking things, thinking we could slow down the drift enough so that software could later compensate for it, but no, it wasn't working at all. So I ended up developing a reference clock adapter that lets you take the output of a GPS disciplined oscillator and feed it into the QDX and essentially get GPS accuracy on the local oscillator. And also done that for the 888. 888 being a receiver, the drift isn't so bad because it's not heating and cooling, but the accuracy and the drift were still noticeable, and we wanted to get better than that. So TCXO, temperature compensated crystal oscillator. They're great, but there are different ways to make them, and sometimes the method being used is not really appropriate for our narrowband ham radio, communications use. That top trace there, ignore the tiny little stair steps. That's an artifact of my measurement, but the big jumps, and that top one is as the temperature was cooling down a little bit and then heating up a little bit. So the temperature went up and down. You can see the oscillator makes big corrections to its frequency. And that hash in the middle, that was where it was just kind of, the temperature was sitting right at an inflection point. So it couldn't decide. It was shifting the frequency up and down and up and down. And it met spec. I mean, the parts per million spec and all that, it was in spec, but you use that to generate a transmitted signal or use it as a local oscillator for your receiver. And that's going to play havoc with your data modulation or demodulation. So don't use that oscillator. The one below is a different type of TCXO. And here, what we're seeing is on top, it was frequency versus time. The bottom one is frequency versus temperature. I have a little temperature chamber I made out of called a reptile incubator. I get it off Amazon. I put a new controller in it. So I could control the temperature and measure frequency. Here you see the curve, a temperature compensation curve. And you'll notice it's not a single straight or curved line. It almost looks like a hysteresis curve. When it's cooling, it's following one track. When it's heating, it's following a different track. And that is something, and even an ovenized crystal oscillator will do this. MEMS silicon oscillators will do this too, the micro machined ones. This is why even an OCXO, you're not necessarily going to be on frequency because it just depends when you turn it on. And I got some more here. Oh boy. Yeah. Notice the top curve. The bottom curves are frequency over time and temperature versus time, just so you can see what's going on. But the top curve shows this, it's called retrace, that fact that it's not a simple curved line, which is, the compensation trying to work. But that's the behavior of the actual crystal. And you can't even really predict it because it depends on the history of where it was when you reversed the temperature swing. So I'm just saying it gets complicated if you want highly accurate frequency references. We kind of end up, GPS disciplined oscillator is really the way to go. I know people that have, cesium standards in their home. I know a guy that has 2 of them. I'm not that guy. The GPS disciplined oscillator is really the way to go. And clock adapters using GPS disciplined oscillators or some of your radio gear has got a GPS stabilized oscillator, and it might be good enough. It's not quite the same thing, but it's close. And these are the adapters that I provide. One of them's got a little phase-lock loop on it because if you only have a 10 megahertz input, but you need a 25 megahertz output because that's what the QDX needs, has a little phase-lock loop to multiply it up. Now, spurious clock output, is that, yeah, that kind of shows up. Hope you can see it. If we have a clock source, ideally it would be a perfect sine wave, no sidebands. You know, harmonics maybe don't matter that much in for a local oscillator, you know, depending on how you filter it and all that. For a sample, analog to digital sample clock, harmonically related spurs probably aren't a problem. I mean, a square wave's got a ton of odd harmonics. But these are non-harmonically related spurs, these sidebands on the spectrum there. And those are due to the type of dividers, basically, that are in the digital synthesis. Again, different dividers have got different spur characteristics, and it depends on what the divider ratios are. It's a whole bunch of work done on that to figure that out. But here we got spurs about 40 dB down, and it's good enough for a lot of purposes, but you can do better depending on how you configure that part. This is the SI 5351 clock generator, by the way, generating these. And it's about $1 part that's used in pretty much every modern radio out there now, or a whole lot of them. And I use them in the stuff I design. So you can reconfigure the way you're using it. You lose some capability, but now notice the spurs, they were minus 40, now they're minus 74. And it varies again, depending on how you have the dividers programmed, but in general, it just shows that all of these things, you know, there are differences, how you implement things, the parts available, the type of divider is really to me, it's a really interesting topic, how they behave. And you can analyze these things much the same way as you could traditional analog mixers. Sampling is just another type of mixing. And you could use the same tools that you use if you were to, you know, do, you know, what's the intermodulation distortion of a amplifier or a mixer, you know, traditional analog ham stuff. And a lot of that same math or concepts anyway also hold if you're doing sampling. Okay, but hey, zooming in, we saw the spurs went down, but they're still there. But now we've got them down at about minus 86 dBc. This is close into the carrier. You could not really see it close in. You can see some hash right near the carrier, but if you zoom way in on that, we've got lots of little spurs. And again, these are divider spurs caused by dividers. So they create interference if they're bad enough when you're transmitting. They can, on the receiver side, other signals that are normally out of your filter range, you know, you're doing post-processing filter in a wideband SDR. You're not filtering the front end, but you're filtering it in DSP after it gets digitized. But spurs on your clock will mix with signals outside of your bandwidth and show up, and you know, then they will pollute the signal you're trying to decode. And the same thing can happen in the transmit side. This stuff is actually pretty symmetrical. You gotta be careful when you're measuring this stuff because a lot of test equipment, no test equipment is perfect. These have their own spurs, their own noise, their own drift. And so it takes a lot of care, and I still get fooled a lot of the time. And so I've got 3 different spectrum analyzers, and I will always sanity check my measurements by, is this really there? If I'm really stuck, I'll take one of my ham receivers and is that actually a signal or is that my analyzer inventing a signal for me? So, resources here, take a look. Again, Turn Island Systems, Whisper Demon, Tapper. I don't have HamSci up there and I should. So search for HamSci. There's a lot of interesting stuff going on and some really smart people. One of the people I relied on, KA7ZOI, guy named Clint, has done a lot of work on filter optimization and 888 analysis. So I recommend looking at his blog also. He's a really good guy. And I think I have run out of, yep. So if anyone has any questions, as you can tell, I'd love to talk about it. And if not, was there a question?
Yes, stand by.
I was just curious. So that was a really interesting talk. So thank you. Just wondering what the noise figures are for your low noise preamplifiers.
I don't have that memorized. If you go to turnislandsystems.com, again, it's my garage shop. I've got specs and the stuff I do isn't technically open source, I guess, but I do have schematics and a whole bunch of test data for almost all of it. So I describe the parts used in most cases for the amplifiers. I have specs for third order IMD, 1 dB compression and noise, although my noise floor measurements maybe aren't perfect, but you can also look at the manufacturer's data because I do describe, I think, the parts I'm using. And is everybody else asleep? No?
Any other questions for Paul?
Well, thank you very much.
Let's have a big hand for Paul.
Appreciate it.